Hi folks, Mr. Long here. We are just going to do a screencast on the fundamental theorem of calculus. Part one we're quite familiar with, I think. Part one is, this right here is the how much the y values change by on an original function, and that's equal to the area under the curve of the rate function between a and b. So again, the area under the curve between a and b is the change in y value of the original function between x equals a and x equals b. We can rewrite it another way where we add f at a to both sides and we replace b with x. And this is where we generate a brand new function. Whoops, that should be a capital there. Capital F at x is f at a plus the integral from a to x of f at t dt. So another way of writing it would be to say that f at x equals f at a plus the integral from a to x for f prime of t dt, right? So if this is a small f at x, this is a big f at x. If this is f prime, then this is f. Okay, so that's the fundamental theorem part one. We've used that a lot. Now, the part two is a really easy part of the fundamental theorem, and that's the inverse nature of derivatives and of integrals. And it's like if I said do d by dx of the integral of 2x. Okay, d by dx of the integral of 2x. Well, the integral of 2x is, so that's going to be d by dx of, what's the integral of 2x? X squared plus some constant c. And then what's the derivative of each of those? 2x. So you can see that if you integrate, then differentiate, they're just inverse processes, and you just get what you started at. That's part two. Okay, part two just is the inverse nature of derivatives and integrals. So there's two parts to it. You're not going to understand it when I write it this way, but you are going to understand it by me going through a few examples. It's very, very straightforward. Okay, so here are our part two examples. So in order for us to do this, I'm going to have to integrate that with respect to t. Okay, the integral of t squared is t cubed, and then divide by 3, right? So it's going to be 3 divided by 3. So that's going to be, I have to keep the d by dx. Then I integrate 3t squared, and I'm going to end up with just t cubed evaluated between x and 4. So I end up with d by dx of x cubed, right? So I'm replacing everywhere where there's a t, I replace it with x. Then I subtract off this part. So it's going to be x cubed minus 4 cubed, which just equals, so the derivative of x cubed is 3x squared, and the derivative of 4 cubed is, that's a constant, it's just 0. So I want you to take a look at what we end up with. So when I'm doing an integral here between 4 and x for 3t squared, and I differentiate that integral, I end up with what I started. Okay, so I didn't have to do all this work, right? I didn't have to do all this work. I just have to substitute in the original equation if this is an x and this is a number. Okay, again, if it's a number at the top and this 4 at the bottom. Okay, folks, because of the inverse nature. And also the fact that when I substitute 4 in, I get 0. So let's look at this one. So for this one here, what I would have to do is I'd have to rewrite this. Okay, so I'd have to rewrite this as d by dx of the negative integral from 5 to x sine of ln of t dt, right? Why did I have to do that? Because I need the x to be up here and the constant to be in the bottom, and I always do the negative of that. So now it's, again, very straightforward. I don't have to write out anything else. I know automatically the answer. I've got that negative, so I have to add in the negative. But the rest of it is just going to be that, replacing t with x. Sine ln of x And that's it. Okay, that's all I have to do, because I know what I've done is I've integrated, then I've differentiated. So I do something and then I undo it. I square root something, then I square it. I cube root something, then I cube it. I take the sign of something and I sign inverse it. I just end up with what I started at. I end up where I started at. Okay? So now there is one that's a little bit more challenging than this. What happens if this isn't just x? Okay, and you're going to see here, it does change things a little bit. Okay, it does change things a little bit. So for this one here, what is the integral of cos t? Well, the integral of cos t is sine t. So sine of t evaluated between x squared and 0. Okay, the integral of sine t evaluated between x squared and 0. So that's going to become, oh, whoops. That's not very good. I forgot my d by dx. I still have this d by dx. Sine t evaluated between x squared and 0. Okay, sorry about that, folks. So sine t evaluated between x squared and 0. So now I need to replace, so that's going to be d by dx sine of x squared minus the sine of 0. Well, I know the sine of 0 is 0. So this is always going to be a constant, so the derivative of that's going to be a constant. How do I do the derivative of sine of x squared? Well, I have to do the chain rule. What's the inside derivative? 2x. What's the outside derivative? Cos brackets. So it's going to be, the inside derivative is 2x. Okay, the outside derivative is going to be cos brackets. It's going to be cos of x squared. Okay, so there's a bit of a change to this one. If you notice, all it is this. Here's the general rule, and it's easier than remembering the formula. If this thing here, if this right here, if this right here is different from x, because of the chain rule, we have to differentiate it, 2x. And then we replace x with whatever was there, x squared. Okay, so that's all. I do becomes the inside derivative, and then I replace it. So let's look at this one. This looks like it's really hard, but is it? Okay, is it? So when I'm going between 1 and x cubed, I know by the chain rule, I'm going to have to do the derivative of x cubed. So this is going to equal 3x squared, right? 3x squared. And then square root of, instead of t, it's going to be x cubed squared plus 7, right? So I'm replacing t with x cubed. Okay, this part's the chain rule, and then I replace t with x cubed, so that my final answer is going to be 3x squared square root of x to the 6 plus 7. Okay, one last question. So we're going to define h of x as this function. Okay, we're defining a new function. And then we want to evaluate h prime at 1. Okay, oh, whoa. Again, Mr. Long. We're going to define that. Sorry. That's h of x, and then we want to get h prime at 1. So now, because we have to this is harder to recognize, but this is a fundamental theorem part 2 question. Because what am I being asked to do? I'm being asked to get the derivative of this. Okay, to get the derivative of this. So what I'm going to do first is I'm going to say that h prime of x is going to equal d by dx integral from 1 to 3x t squared plus 4 dt. So what I need to do now is to do this, to just rewrite it. So remember, when this right here is anything other than just plain old x, I have to do the chain rule. So what's it going to be? Well, the derivative of 3x is just 3, and now I'm going to replace t with 3x. So it's just going to be 3x squared plus 4. Okay, so it's going to be 3 bracket, 3 squared is 9, x squared is x squared, plus 4. And that, folks, is h prime of x. And now what I do is I substitute in 1. H prime of 1 is going to be 3, 9 plus 4. Why is it 9 plus 4? Because 1 squared is just 1. 9 plus 4 is 13. 13 times 3 is 39. H prime at 1 is 39. Okay, folks? So that's one that you had to, there's a question just like that on one of the mock exams, and so I thought I would do that. So these ones are really quite easy once you get the hang of it. All right, folks, so we'll stop there, and hopefully that gave you a bit of a sense of what the fundamental theorem part 2 is all about.